How many people have kids? I can see some hands. Okay. How many people have multiple kids? How many people have ever tried to get those kids to sit still for a family photo where everybody's smiling, eyes open, and they're not hitting their brothers or sisters? Yeah, it's nuts, isn't it? I've got 4 kids. You can't get them to do it. And I guess it's sort of, I guess I'm doing penance for when I was a kid. I was one of 5. And we did the family group photos. So when you've got a group of 7 people and 5 of them are children and siblings, it does not go well. There's always somebody who's yawning or their eyes are closed, and then like 20 minutes into the photo session, somebody's arm is touching somebody else's arm, and you're looking at someone the wrong way, and people are crying. At least that's how our family photo outings went. And there were a lot of them. My parents love photography, and so my dad, every time we had a family get-together or vacation, would put this big, giant gray bag over his shoulder with like rolls and rolls and rolls of film, and he'd have the huge camera hanging from his neck, and he'd walk like this. It was a very heavy bag. I don't know, that can't possibly have been healthy. And then he also had the tripod that he would carry with him. And at some point in every trip, the tripod was coming out, and the tripod was going to get unfolded and set up. And when you saw the tripod come out, that was your tip that you had to go run and get a snack really quick because you were going to be spending the next couple hours in front of this tripod trying to get a photo taken. And it wasn't just the group photos, like that would have been bad enough, but they felt like they needed to have every possible combination of us. We had the group photos, then we had the photos of all the siblings, then we had the photos of the brothers, and then the sisters, and then the aunts and uncles, and then the cousins, and then whoever happened to be wearing green shirts and blue pants or whatever it was. Every single arbitrary category they could come up with, that's what we did. And so the outcome was that we had shelves and shelves and shelves of these photo albums. Now, we never went full film projector mode on anybody when they came over and you make them sit down and watch all the photos through the film projector of your vacation. But we came close. The photo albums came out quite a bit when people came over. That's probably why we stopped having as many visitors later on. But I got to admit that I kind of enjoyed part of it because there's something cool about looking through a bunch of photos. There's something cool about it. There's something really neat about being able to be reminded of memories that you had a hard time recalling. They're just below the surface, or being able to see relatives that you haven't seen for a while or maybe have passed away, or being able to see photos of a younger version of yourself, although sometimes that can be actually a little bit iffy if those photos are photos you'd prefer not to have out there. That's me in my fanny pack. Jason, that's not good. All right, anyway. I didn't know he was going to be here when I prepped it. No, so photos are cool. And people love images. Like, images are very powerful things. That's what they do. They connect us to places, to moments, to experiences, to people, whether we know them or not. Images can move us on a very deeply emotional level. And that's why I think we're so enraptured with them as a society, and why now with the mobile phone that has a camera on it, everybody walking around is an amateur photographer, cataloging every possible moment of their life from every possible angle. And I do mean this isn't an SNL thing. This is apparently a real product. You can order this. It is for taking selfies of your backside. I did not know that there was such a demand for this. I cannot vouch for this product. I have not tried it. It didn't arrive before I left. Well, Bruce says it's excellent. So you can question whether this is of value, right? Like the backs of the Belfie. God, it feels wrong to say, the Belfie. You can question how valuable it is, but you can't argue that people are doing this, that we're taking an incredible number of photos now. In 2012, 10% of the photos ever taken in the history of photography through that point were taken in that single year. And I just want to hammer on that for a second because it blew my mind. Modern photography was apparently invented as we know it in 1839. So from 1839 to the end of 2011, that's 172 years, 90% of the images were produced. In 1 year, we put another 10% on top of that. That's crazy. And we're sharing those photos at an incredible rate. We're sharing 1.8 billion photos per day, according to Mary Meeker's 2014 Internet Trends Report, to sites like Facebook and Twitter and Instagram. And this abundance of imagery is being reflected in the makeup of our sites. Our sites are up over 2 megs right now, and 1,300 kilobytes of that is image weight. It's more than all other resources combined. In fact, it's nearly 63% of the average website is images. And obviously, there's performance repercussions of this, right? And we know sort of some of the obvious ones, right? That it adds weight to the page, it adds requests to the page, and those things slow things down. But that's just what's happening on the surface. There's a lot that's going on under the hood. The browser has to do a lot of work to get those images to actually show up on our screen. So this is the Velocity site as loaded up on my Moto X. And I'm not actually picking on the Velocity site because they do anything particularly bad. They actually don't. They just have a very similar design pattern to what you see is pretty common, which is this hero image is a very popular thing in the web design community and trends right now, is this big hero image that kind of scales down for smaller screens. Now on my Moto X, this is taking up a space that is 360 by 202 pixels, all right? Now, of course, that's not the size of the image being passed down. The size of the image being passed down in this case is 1280 pixels by 520. Again, not picking on them necessarily. It's a very common thing. The browser grabs this image, and it can't just shove this up onto the screen. It has to do a lot of work. It has to request and download the image. It has to go through a decoding process. It has to copy that decoded data over to the GPU, and then it has to put that out onto the display so that you can actually see it. It's actually a fairly intensive process. And we know kind of what's going on in the request stage for the bandwidth latency sort of constraints. I think those are pretty well discussed at this point, and if not, feel free to follow up afterwards, and I'd be happy to talk about those. So I want to kind of skip ahead and jump into the decode. So this image of Lara, it's a 1280 pixel wide JPEG. And so let's start with looking at the JPEG decodes. We're actually going to spend most of our time on JPEG decoding process. Because two reasons. First off, if you look at the image formats in use on the web, JPEG kind of rules the web still. It's nearly twice as much as the next closest image format at the moment. The other reason why I want to spend a little bit more time on the JPEG decoding process specifically versus PNG or GIF is because there's actually more interesting things going on from a browser perspective. They're doing more things to optimize that process currently that are only being applied to JPEG format versus something like PNG or WebP or anything like that. So when you're talking about a JPEG image and you create a JPEG image from your favorite graphic editing program, it goes through an encoding process. It starts with RGB data, which it converts to a YUV color space, does the chroma subsampling, some quantization, Huffman encoding, maybe a little bit of other processing there for some compression, and eventually spits out the image that you actually save on your disk. So what the browser has to do with this image that's been produced is reverse this and walk backwards through the entire process. They have to do the decoding, the dequantization, the upsampling, and they have to convert the YUV to RGB data so that they know what to put up on the screen. So this is all quantified inside of a decode time, which is exposed in some developer tooling. Chrome does this. They will expose right inside of the timeline. That the image decode, you can actually filter in the search box and just search for just the decoding times and find out how long it's taking each image to decode. They also have the paint profiler, which sometimes gives you a little bit extra information about how that's going on. This is nice. It's nice and simple. It's easy to get to. There is a more advanced expert, I don't know if expert's the right word, but more advanced, intense way of looking at this stuff that the Chrome gang turned me on to, which is Chrome tracing. So if you go to Chrome://tracing, you can take a very detailed profile and trace of what the browser is actually doing, exposing a lot of the things under the hood that you don't get through developer tools. When you do this, you end up with a very intimidating screen, in my opinion, of all sorts of charts and gray bars and numbers down at the bottom. Honestly, I feel like it's a little cumbersome when you're first getting into it. And actually using it for a while, it still feels a little cumbersome. But the amount of information in there is impressive. So if you go up to the top right, there's a search bar there. And you can actually start to, again, filter down by the task. Now, what we're looking for inside of Blink is called decode and scale. That's what it actually reports inside of the developer tools. And when you tap that in, it'll filter out down here at the bottom and tell you just how much time total was spent on that particular task. So in this case, we can see that for the velocity side, it took about 20 milliseconds on the CPU is how much time was spent doing the decoding and the scaling. The scaling would be the resizing. It used to be a separate process. It's now baked into the decoding process. The other nice thing about the Chrome tracing is that once you get to these ugly-looking gray bar things, you can zoom in on those, and you get a nice little stack, a very visual, colorful stack of all the little tasks that are going into it. And this is why it's sort of the advanced view, because there's you can drown yourself in the amount of information that's provided. I will say that if you are looking at this and you're like, I don't know, this feels a little, I mean, some of you are probably geeking out on this and using it right now. Others of you are probably looking at this like I did the first few times, which is feeling completely overwhelmed. I still advise playing with it and getting into it because there's so much great information. Don't let all the different tasks and threads and things throw you off. It's pretty powerful, and you can find a lot of useful insights out of it. So this is what Chrome will provide. Internet Explorer / Edge actually also exposes decoding inside of their developer tools, which is nice. It's very clean, very easy to understand, and they give you a nice duration in terms of for that particular image. It's a nice breakdown. It's very easy to use. Firefox doesn't expose anything for decoding time, and nor does Safari, yeah. So we're going to move on. So now that we know how to track it, what I wanted to do is I wanted to see what is the impact on decoding when we're using different size images and asking the browser to resize those down and scale it within the browser. So I created a couple rough, crude test pages. Basically, the idea, very well designed. Basically, the idea is that I've got a bunch of images and I'm sizing them to 200 pixels wide. That's what I'm telling the browser to display them at. But on different pages, I'm providing different sized images. So on one page, I've resized all the images to 200 pixels. On another page, I've resized them to 400. So we're doing like a double, sort of like the compressive technique that a lot of people use for retina images. And then I've got one that is large size. What I did is I kept it at 6 times what it needs to be displayed at. So they're all 1,200 pixels by 1,200 pixels. Big images, but it doesn't take you very long of auditing around the internet to find a few sites that are doing the exact same thing. And if you fire this up on my Air, which is a very powerful machine, what you get is the resize, the appropriately sized, only spends about 8 milliseconds on the CPU doing the decoding inside of Chrome. Once you double it, you're starting to serve those 400 pixel images and telling the browser to shrink it down. That jumps up to 26 milliseconds on the CPU. Once you start going larger than that, and you get to that what we were talking about where it's 6 times the size, it jumps dramatically to 266 milliseconds. In a percentage world, since that's sometimes a little bit easier to understand, it's a 235% increase by doubling the image, just going from 400 to 200, and a 3,000% increase in CPU load by going to these 6 times images. Of course, this is about mobile image processing, and those mobile devices have a lot more interesting constraints when it comes to a lot of this stuff. So I also ran this on a Nexus 4. And I chose the Nexus 4 partly because it was convenient and handy, but also because I didn't want to choose something that came out right now. Like if you're looking at like an iPhone 6 Plus or like the Moto X2 or things like that, those are the devices that maybe we are using, and they're very popular amongst a certain crowd. But it's not something that's very indicative of what our users are using. Just because we're updating constantly doesn't mean that our users are. The Nexus 4 is a little older, but it's still a pretty powerful device. It's still got 2 gigabytes of RAM, a decent CPU and GPU attached. It's not a bad device, and it's a little bit closer to what a user down the road might be using, with the exception of maybe the RAM, which is a little higher, which we'll see in a little bit, than what might be typical. But profiling on a Nexus 4, the exact same scenario. Appropriately sized images, so we're not telling the browser to do any resizing, just decode it, suddenly jumps up to 30 milliseconds. If we serve them double images, we're up to 100 milliseconds. And brace yourselves. If we go to 6 times, if we take a 1,200 pixel images and shove it down to 200 pixels, it spends 1,535 milliseconds on the CPU doing that process. Again, looking at it from a percentage perspective, that's a 230% jump and a almost 5,000% jump in terms of the load on the CPU for those large images. It's at this point, when I was preparing for this talk and running these numbers, that I ended up looking very much so like this, because I was like, what the heck? That's a lot of CPU. That's a lot of stuff that you're throwing on the device there. So this is going to sound hopefully very simple and very like it's something you've heard a million times before, but I'm going to say it anyway because it's not always done, and it's massively important, but please, the rule number one of image processing and optimizing is resize those images. And I wanted just to hammer that home. I was trying to think like how could I reiterate how serious I am about just making sure that this simple thing never doesn't happen. And I got a clue from when my friend Katie did karaoke, slide karaoke the other night, and apparently she mentioned that she did not like cats, and it incited a near riot. I don't like cats either, so this is actually no skin off of my back, but I'm going to threaten you all with like this kitten. The things that will happen to this kitten if we don't resize images are not good. And again, I don't like cats, so it doesn't bother me. So think about the kittens. So jumping back into the process here, that's the decoding and decoding time. We're going to come back to a little bit because there's actually some good news there, which we'll come back to in a second. But first, let's jump to the idea here of what we're getting stuff over to the GPU. See, once that image is decoded, at that point, the browser wants to store that decoded information inside of the memory so that it doesn't have to go through the decoding process again. It makes sense. That's intensive stuff. So if you look at something like this image, and we break it down, every single pixel inside of that image is going to end up with an RGBA value attached to it so that you know what the browser knows exactly what to paint in that particular pixel. So traditionally, what we've been able to say is from a memory perspective, to find out how large of a space the image is actually taken when decoded, it is the width of the image times the height of the image times 4, RGBA. Which means that when we're passing something like this, a 1280 pixel wide by 520 pixel wide image, if we apply our itty bitty little bit of math, that's taking 2,662,000 bytes. That's 2.54 megabytes on the disk for the decoded image. The velocity site as a whole, we actually can get inside of the memory information is not exposed very well at all by Chrome or Safari. Firefox has about colon memory, which does a really good job of detailing the memory, like telling you exactly where the memory is being spent. In this case, the images, and if you drill down, you can actually see specific images. I don't have a screenshot of it, but the Edge tools actually do a fantastic job of this. Which, by the way, if you haven't checked those things out lately, it's totally different than the old days of Internet Explorer. It's good stuff. Highly recommend it. But when we look at that, we see it as 23.11 megabytes are being stored on the disk in decoded images. The implications of this are kind of interesting. Yesterday at I.O. during, I think, one of the keynotes, Jen Fitzpatrick, who was the VP of Product Management at Google Maps, got on stage, and she was talking about some of the things Google's trying to do to try and attract or reach a global audience and what they're doing in terms of reducing bytes and memory implications on these devices. And one of the things she said was that 25% of new Android phones have only 512 megabytes of RAM. Now, the 23 megabytes dedicated to those images on Velocity may not sound horrible, but and I don't want to reveal who it is, but there's a couple news sites, very popular news sites, that when I was profiling this, were hitting about probably 40 to 50 when you actually did the calculations. That's how much they were potentially throwing inside of memory just for the images on one page. So if you consider that you've got a phone with 512 megabytes of RAM or less, because look, this is new Android devices, right? There's much less powerful devices out there. That starts to add up very quickly when you consider that the browser and or the operating system is actually needing that memory for so many other things. Which is another reason, by the way, why the resizing makes sense. Because if this was passed down at the correct size, we're only taking up about 290,000 bytes. Or, doing a little bit of math, we end up saving 2.26 megabytes on the disk in terms of memory implications by serving the appropriately sized image. This also extends into things like sprites. If you look at the sprite for the LinkedIn Connect widget, this is what you get. It's a 270 pixel by 936 pixel image. And there's a lot of blank space there that if they could condense that, you're probably going to be able to reduce your memory impact by about, I don't know, about 30, 40%, I'd say. So when you're doing things like that, it also means you want to consolidate and get that stuff as close as possible. So again, this gets back to that same idea, that same basic principle, but it's worth saying again, remember the kittens, because that's such an important thing. The other interesting implication of this is if you start to dig into this in different size images and seeing what the impact is for size, that's when you start to get the really interesting nuggets. So if you take a 600 pixel wide image and a 200 pixel wide image, and if we resize them both by only 50 pixels, so we're not shifting very much. Like in the grand scheme of things, resizing an image by 50 pixels is really minor. But I still want to show it because what it's doing is it highlights something that I think we can actually apply when we're actually building our sites. So by shifting from 600 to 550 pixels, we end up with 230,000 wasted bytes. By shifting from 200 to 150 pixels, we end up with only 70,000 wasted bytes. Even though the breakpoint feels like it's about the same between, we're only shifting every 50 pixels or so, the implications in terms of decode time, the implications in terms of memory use is significantly different. So, and that was a 50 pixel shift. So if you're taking like a 1,000 pixel image and you're shifting it down to 600 pixels wide, you're wasting a ton more memory than you would be at any sort of sizing at a smaller scale, at a 250 down to 100 or 150, whatever it happens to be. So if you're looking and doing like responsive design at all, if you're doing some sort of breakpoints in terms of your image generation and serving different size images to different screens, you want to get a little bit more aggressive on the end. Instead of like a pretty evenly spaced out set of breakpoints for your images, you probably want to get a little bit more intense as those images get larger so that those larger images aren't doing much resizing, because you're going to minimize the memory impact and the CPU load on that. So, this is, I think that hopefully this is hammering that it's a lot more than like the network side of things. In fact, the impact that we're having here is impacting the memory, it's impacting the battery, because what's happening is if you're constantly using that CPU and GPU and communicating back to each other and doing the decoding, you're constantly eating up that battery. That's why if you load up a very image-heavy site and you float through, it's probably getting kind of hot. The life of device, again, that's not healthy when you're burning your hand with your phone, as it turns out. And the overhead on the CPU, GPU. There's a lot of things that's happening when it's doing those image processings that have, so images have a huge, huge impact on the device and how it's performing as a whole. So at this point, it's tempting to, well, at least for the developers maybe in the room, it's tempting to say, let's just go back to Times New Roman on a white background. Any designers in the room are about to throw me out. We can't do this because, like we talked about, images are important. Images matter to people, and they're very powerful things. Thankfully, there's good news here. Thankfully, the browsers are figuring some things out here that are very helpful, and there's actually some things we can do to help the browser along with some of this stuff. So if we go back to our process here, let's zoom in on the chroma stuff and the YUV to RGB. I'm going to get maybe a little kind of in the weeds on some of the color stuff here. I will say that it took me a long time to wrap my head around it, so don't feel bad if, I'm not going to be at all offended if I walk through this and at the end you're like, I don't understand any of that. Hopefully you get the takeaways at the end. I'm going to do my best here, though. So when you look at an image, the way that we process it, we break it that there's light and there's chroma, the color stuff. So luma for light, chroma for color. We are more susceptible to the light side of things. So if the light is a high resolution, that's where we're getting a lot of our detail from. So the chroma, you can actually do a lot more compression on the chroma channels without us visibly being able to tell, without us being a huge visible difference. That's kind of the whole premise around the YUV space and the chroma subsampling that's going on. YUV, or YCBCR, depending on, I think one's digital, one's analog, basically breaks out an image into a luma channel and two chroma channels, which one is the difference of the blue and one is the difference of the red. That's where you get your YUV thing. When you're looking at this, now the optimization that takes place within a JPEG on this level is called the chroma subsampling. And if you've ever got into the nitty-gritty on that stuff, the chroma subsampling always looks like 420, 422, 444. It's basically a JAB. Where J is like the size of the width of what it's doing in terms of which unit it's doing the subsampling on, what the size of it is. A is how many samples on the first row. B is how many different samples on the second row. That probably is clear as mud, which is why we're going to do a couple examples here now. So let's say that this is our image, and they're all pretty clearly defined colors just so we can highlight some of the color degradation things here. But we have an 8-pixel image, 4 pixels wide, 2 pixels high. And we're going to apply some chroma subsampling to it. Chroma subsampling almost always starts with a 4. I don't know if that's like a mandated rule. Everything that I was reading was saying that it's almost always, so I assume there could be an exception, but I have not seen it. So what that means is that basically if we take this, we're going to be processing a 4-wide area at a time. So when we create our Luma channel, what we do is we want to keep that high resolution so that we don't perceive the loss in quality nearly as much. So we are actually taking the Luma value for each pixel in that 4 pixel by 2 pixel area. So our Luma channel has 8 distinct pixel values as we're going through here. The A and the B starts to get into the chroma stuff. So a 444, which is basically nothing, no subsampling basically applied. You're taking this same area, you're going 4 across. The second 4 tells you that in that first row of 4 pixels, you're going to take 4 values out of that row. The second 4 tells you that in that second row of 4 pixels, you're going to take 4 different values than what you have in the first row. So you end up with 8 total. So your chroma might look like this, your chroma channel, and when you apply it back to your Luma channel, it ends up being basically exactly what we had before. 422, so let's start to break it down a little bit and actually start to apply a little bit of compression here. 422 says we're going to take this, we're going to go 4 across, we're going to take 2 samples out of that first row. The second 2 tells us we're going to take 2 different samples now in the second row. So if we've got, so we end up with about a 50% savings. So if we look at this image, we're going to take a sample, 2 samples for the top, 2 samples from the bottom. And now that's why the colors are different, so hopefully you see that we're losing some color quality here. We're losing some degradation. We're ending up with an image that is a little bit different, or in our case, a lot a bit different, but in photos, it's a lot less noticeable. There's a 411 level, which I don't think is particularly common. The 411 basically says we're going to take 1 sample for our first row of 4 pixels, and we're going to take 1 different sample on the following row. We end up saving a lot here. We end up getting a 75% savings, but of course there's a huge cost in that, because now we've basically turned our chroma stuff into this. And our final image is dramatically different. And again, in a photo, it's going to be less impactful, but you're going to start to see some things here, some artifacts. 420, which is the last one I'm going to go into, and also the most important one for reasons we'll get into, because it's a little bit more common, I think, in graphic editing programs, and there's some good ramifications here. 420 says, again, we're going to take that 4 pixel wide area. We're going to take 2 samples from the top. The 0, this is where we finally get to see what that second one kind of does. The 0 says we're going to take 0 different samples from the first row. So in other words, we're not going to take any samples in the second row. We're just going to take those samples from the first row and extend them down. So again, we get that huge savings. But again, we have more serious loss of quality, more degradation in the final image. This is a really powerful thing, actually, once you start to kind of wrap your head around it and the implications of what it means when you've got the YUV, when you're storing the data in YUV instead of RGB, and you can apply those chroma subsamplings. And so the browser started to catch on to this, and I'm pretty sure Internet Explorer was the one who led the charge here. Because as far as I can tell, they were the first ones to do it, and they had a great post about this, about what they were doing here. Basically, they decided that what you could do is you could actually break some of that decoding up and have that happen on the GPU. So remember, we're storing in memory after that first decode before it gets copied to GPU. By pushing the chroma upsampling and the YUV to RGB conversion onto the GPU, the stuff that we're storing in memory is no longer width times height times 4, because we don't need that much data anymore. The formula becomes a lot more complicated. It's width times height times 3, because you have YUV, and then width times height times the subsample level times 2. Don't worry about it. It's just there for the few of you who want to do that and punch out your calculators and stuff. Most of you probably don't. The implications of that are interesting, though. So here's Lara's image, right? And we've got the RGBA value. This is what it was stored on in disk. This is what happens when the decoding happens entirely on the CPU. Each of the subsequent ones after that are with the different subsampling levels applied. This is now how much space it actually takes in memory on the when you've actually got it decoded. So the 420, if you apply a 420 subsampling, you end up with a 62.5% savings in terms of memory, which is a huge, huge deal. Which is why another great thing to take away from this is make sure that you're trying to get your JPEGs whenever possible to that level. It's pretty easy to do if you're using like Photoshop or anything like that. As long as you save for web at 50 or under, it saves in a 420. If it's 51 or above, it's 444. But anytime you can get it down to that 420, you're going to save yourself a ton of memory usage on those devices, which is, it adds up. And it's especially important when you start to factor in the image pooling that these browsers are doing. This is a profile from, can you tell? No, good. This is a profile from a popular news site. The decoding images, as you can, all these little green dots are basically all these images that have been decoded. And this was me scrolling down to the bottom of the page, and I paused for a little bit to give myself a nice little gap. And I started to scroll back up. And all the decoding, like for quite a few of the images, starts to happen again. And in fact, if you dig into this, what you find is that it is the exact same image. This one is 3.26 milliseconds spent on this climate change image that was near the top. And then again, later on, we see another 3 milliseconds spent doing the decoding on this. So why are we decoding the same image twice? Well, this image, if you do the math, it's spending a little bit over 26 megabytes to 27, somewhere in that range, in terms of what the images would be decoded in memory. What the browser does is the browser says to the operating system, hey, you know what? This image was way up here, and I've scrolled down here. It's no longer visible. You know, it's long gone by now. Does the operating system need a little bit of memory? Does it need something from me? If so, you can take this. And if the operating system says, yes, I will take that, and I will use that for other things that I have going on, other processes or other things going on, the browser has now lost the decoded image. So now if it ever has to get to a point where it might pop back into that viewport, might pop back into being visible, it has to go through the decoding process again. It has to go through all of these steps again and make sure that it gets it back into data that it can actually use. It has to happen. It's a necessary thing because otherwise you're going to be breaking devices left and right. But that means that that 62.5 memory savings that we're getting is huge. It's a huge and wildly important thing because if we can avoid that extra decoding, we're avoiding even more overhead on the CPU. We've basically doubled our CPU when we have to get into that situation where we're using so many images that the browser has to do this image pooling. So again, Internet Explorer led the charge here, I think on IE 11. Edge does it, I think, basically everywhere. But the Chrome Blink group got on the bandwagon as well. So remember this this test case we had where we had like the 8,000 or 5,000 increase, and it was spending 1,500 milliseconds doing the decoding on the CPU. They have GPU decoding enabled in certain scenarios. If they don't have multiple rasterization threads, so it is not a device that is apparently powerful enough for them to have rasterization threads, which they've deemed as a better solution for speeding things up. And if the device is, I think, Android 4.4 and up, or if it's a Nexus device. And finally, the most important bit, if you have this on your page, if you use your old friend, the viewport. If you have this viewport tag on, it suddenly will trick that into actually decoding to doing the YUV process that we talked about instead of putting it all on the CPU. So with that enabled, not only does the site look a lot better, yay responsive, but the sizing times come down quite a bit. So we were spending 30 milliseconds resizing before for, or decoding before for appropriately sized images. That falls down to 5 milliseconds. We were spending 102 milliseconds on the CPU for double-sized. That falls down to 27 milliseconds. And we were spending 1,500 milliseconds for large images, and that comes down to 462. Now, these still are pretty substantial. Like 462 is still a scary number, and the percentage increase is actually obnoxious. I did run this multiple times. I'm not sure why the percentage increase is so much higher when GPU encoding or decoding is enabled versus not. It's like a good 3,000% higher, and I'm not sure what that is. It could still just be anomalies. Maybe I just need to run the test more and kind of even that out. but you still get those sizable increases. So it's not bailing us out, this technique, right? It's not necessarily getting us off scot-free. We can't just all start overloading our pages with images of cats and dogs. We still have to be very careful about this. And one of the things that I was worried about when I first started researching this was how much of this was going to be things that really significantly mattered. I was worried that there was going to be a series of micro-optimizations, things that kind of, getting into the weeds a little bit. And I think that when you get down to a certain size, that's probably true. Once you start getting to, if you're doing the resizing the images appropriately and you're not overwhelming those devices with a ton of them, yeah, you're probably getting where you're starting to fiddle between, the difference between 7 milliseconds and 20 milliseconds or 30 milliseconds or whatever it happens to be. But I still think it matters. And the reason I think it matters is, I think, kind of summed up very well in this quote by Jeff Veen, who said, we were talking to him recently about performance. And one of the things that he said that stuck out is he was talking about the difference between 15 years ago and now. And he said, you know what, as bandwidth grows and processing power grows and browsers keep getting better, we just keep filling it up. We're not so it's tempting to look at this stuff and say the browsers are getting smarter, the machines are getting powerful, we're getting more RAM. But and so maybe these things don't matter. Maybe we don't need to worry about how hard it is for those devices to decode and process and how much memory space they're taking up because those things are getting more powerful. But at the same time, we're seeing a trend where we're shoving more and more things onto our client devices and expecting our device to just hold up. We're starting to do more and more intensive JavaScript. We're starting to do animations. We're starting to do more and more content, more and more images. So I think that these things still do matter because we're asking our devices to do a ton. And if I can shave 50 milliseconds, 60 milliseconds of CPU overhead and 2 megabytes of memory, I think that's extremely valuable. Images are huge. Images are such a large part of the makeup of the site. It goes beyond the network, and it starts to tap into the memory. It starts to tap into the battery life. It starts to tap into the life of the device itself, how much overhead is on the CPU or GPU. But thankfully, the things to use, the techniques that we can use to address these things aren't that complicated. We resize the images, make sure that they're appropriately sized so the browser doesn't have to do too much decoding and scaling. Make sure that if for the larger images, you have a little bit tighter breakpoint, and so therefore minimize the impact that that's going to have in terms of memory. Meta viewport is your friend. Make sure that that thing's in there and kick that over to the GPU decoding inside of Blink. Use the 420 subsampling whenever possible and reap the 63% memory gains. These are not particularly complicated things, thankfully. But they're going to have a huge impact on the wear and tear on the device and also an impact on how quickly those operations take place and how quickly your site feels to the user. Thanks. Time? So we got time for questions. Yes, sir. Yes, right here. Decode times of baseline versus progressive. I'm actually not sure. I know that there was a really interesting white paper that got into a lot of detail on a lot of things by actually somebody on the Blink/Opera group when they were exploring whether or not this made sense for them to do. It's like I actually have it printed off in my bag. It's like 30-something pages. That's pretty intense, and it goes into great detail on that stuff. So maybe it gets and hints at some of that. I'm not sure, though. I guess I haven't seen that particular information. That would be interesting, though. Yes, Jason.
In the research, was there anything that you came across that talked about images being sized to be divisible by 4 or 8 or 12? Somebody pointed me information about compressing better, and
yeah.
it was all in French.
It was all in French?
Yes.
So what was the problem? You couldn't read it? Okay. No. Sorry. Well, I think that's your fault. So. I know, Jason, by the way, this isn't a random attendee that I'm harassing. I just want to make sure. So the rest of you, feel free to ask questions. I won't be mean. No, so the question was around if I had seen anything around images sized to a certain factor, like a scale.
Divisible by
Yeah, divisible by a certain number, compressing better. Yes, actually, from the when you're producing the images through like Photoshop or whatever it is, I think it is an 8-pixel. If it's divisible by 8, it does compress better. And you can actually test this out if you create a JPEG inside of Photoshop, and make sure that you've got it so that it's not divisible by 8, and then just cut off a couple pixels, or even add a few pixels, and you'll still see the size is actually the produced size is smaller. I didn't get into that with any of this. I was more focused on the device stuff, so I don't have it fresh in my head, so I'm not sure why that is. But I have seen that. I know that there's a good article inside of, it's an older one, like 2012 or something like that, from Smashing Magazine that went into great detail on JPEG and ping optimization advanced that got into things like that. So that's where I would look, and if I find it before you, I'll send it to you.
Thank you.
One more question. Oh, right, yes.
So there's a bunch of tools where you can set the JPEG quality, right, from whatever 40% to 90%. So what's the relationship between this overall JPEG quality and the subsampling that you talked about, which seems to be very discrete, 4.420?
Yeah. What is the difference between the what is the relation between the subsampling and the levels that you're saving the JPEG at? I actually don't know off the top of my head. If you come up afterwards, though, I'm pretty sure that I have that in the in my bag, and I can probably find it in a few seconds for you. And for those who might have been wondering the same question, I will happily tweet that out afterwards and hashtag a VelocityConf so that you can get that as well, because it's a great question. I should have had that in there. All right, well, thank you. If there are any more questions, feel free to come up afterwards or catch me in the hallway. I'll be here all day. So thank you.